Closing a kitchen cabinet feels like a low-tech interaction. To the casual observer, the mechanism holding it shut is an assembly of molded plastic and a small block of iron. But inside that plastic shell, you're looking at a core of reactive rare earth elements like neodymium and samarium cobalt. Standard iron cannot generate the necessary magnetic pull in such a tight space. Neodymium packs high attractive force into a microscopic footprint, allowing the latch to grip the door tightly without taking up significant shelf space. The hardware you overlook every day is a housing for specific materials that rarely appear elsewhere in a residential environment. These rare earth metals aren't forged in a furnace or cast in a mold like traditional steel. Instead, they begin as an ultra-fine reactive dust. This process is called sintering. The microscopic particles are crushed together under immense industrial pressure and subjected to intense heat, forcing the dust to fuse into a solid magnet. But this fused structure has a significant vulnerability. Neodymium is brittle and prone to oxidation. If you expose a raw sintered magnet to the humidity of a typical kitchen, it will corrode and crumble back into useless dust. This diagram shows how engineers prevent that failure. To keep the core intact, the magnet is sealed inside defensive coatings. This usually involves a triple layer of nickel, copper, and nickel, or a rigid shell of titanium nitride. The magnet's functional life depends entirely on these barriers. Without them, the core would revert to its original chemical state. Holding a cabinet door closed requires managing two forces: the leverage of a wide swinging panel and the kinetic energy produced when that panel slams shut. This diagram illustrates the power density required. A 12mm component generates 14 kilograms of pulling force, like hanging 3 bowling balls from a dime. When pulling a solid door, you use leverage. The tiny catch counteracts that torque with a concentrated magnetic field. Under normal circumstances, two hard metals colliding with 14 kilograms of force would create a sharp impact that could eventually damage the cabinetry. To manage this, designers embed micro-rubber, sound-absorbing buffers into the assembly. These anti-collision paths compress on impact to deaden the acoustic sound wave. Physical pulling power and acoustic dampening are balanced within a single millimeter of space. It is easy to assume that a magnetic field naturally radiates outward in all directions, like light from a bulb. But engineers can steer that invisible force using structures like a Hellbach array or multi-pole magnetic rings, arranging multiple small magnets in a specific geometric sequence. This diagram shows magnetic field lines being redirected. By aligning the poles in a precise sequence, engineers warp the field so that the magnetic pole is concentrated onto a single functional surface, while the backside remains inert. This focused power makes the hardware less intrusive. Modern catches can be embedded flush directly inside the wood grain or mounted to glass panels using UV curing adhesives. In push-to-open systems, the magnet is a trigger. Paired with a concealed kinetic spring, pressing inward releases the tension and ejects heavy drawers outward. In these systems, the cabinet catch operates as an active, energy-storing kinetic engine. Behind the latch in your kitchen is a global supply chain. The factories engineering these components operate on a broad industrial scale. This illustration compares a standard cabinet latch with a massive industrial concrete formwork magnet. They share the same origin. The catalogs that supply kitchen drawers also manufacture magnetic tools for heavy-duty industrial lifting and concrete construction. They even produce specialized agricultural tools known as cow magnets. Farmers have cows swallow these pill-shaped magnets to catch and hold stray nails or fencing wire inside the animal's stomach, preventing internal injury. We often view the door latch as a static piece of technology that was perfected decades ago, but this simulation shows the reality of modern design. Using finite element analysis, engineers run wireframe stress tests on these mechanisms, mapping structural strain to optimize the magnetic pull. The pursuit of a silent, flush closure has turned this hardware into a subject for constant iterative engineering, using simulations to refine the physics of a movement we rarely think about.